Hello, everybody. Welcome to today's crime seminar. Today we have one speaker, one talk. Our speaker is Pengpeng Xiao. She will be giving a talk on quantum DeepONet neural operators accelerated by quantum computing. Pengpeng Xiao is a final year undergrad student in the Department of Physics at Fudan University. Her research focuses on scientific machine learning and AI for science. Pengpeng has conducted research as a visiting student in the Department of Statistics and Data Science at Yale University under the supervision of Dr. Lulu. She has also collaborated with Dr. Peng Chen at the School of Computational Science and Engineering at Georgia Tech. With that short introduction, the floor is yours and you can start your presentation.
Yeah, thanks for the nice introduction and also for the invitation to join this seminar. Today, I'm going to talk about quantum DeepONet, which combines quantum computing with operator learning. Okay,
Yes, great.
so we use quantum layers as building block, and our methods can achieve quadratic speed up compared with classical methods. And I would like to thank my collaborators, Hu Qing and Ran, Dr. Yang and Dr. Lu here. So let's start. My talk will follow this structure. First, we will give a brief introduction on quantum computing and quantum mechanics, and then we will go into the detail of our proposed methods. In the third part, we will present the training and ideal simulation results to show the feasibility of our methods. And in the last part, we will introduce the concept of quantum noise and demonstrate the impact of quantum noise on our methods. So many of you might heard of Schrodinger's cat. Imagine a cat in a box with a mechanism that might kill it. So the cat is both alive and dead at the same time before we observe it. So after the observation, it will switch to one of these two states. This thought experiment is designed to show the counterintuitive idea of superposition in quantum physics. Quantum physics is a fundamental theory that describes the behavior of nature below the scale of atoms. In the quantum world, we deal with uncertainties and probabilities rather than definite outcomes. And quantum computing makes use of these unusual properties to solve problems faster than classical computers. These could include applications in areas like machine learning, where quantum algorithm can offer significant speed up. So recent advances in quantum neural networks have shown that quantum computing can significantly accelerate the accelerate machine learning tasks. For example, quantum neural networks can achieve quadratic speedup in reinforcement learning and online perception. And in linear system solving and least square fitting, the speed up is even exponential compared with classical methods. This opens up new possibilities for solving problems in machine learning. However, the usage of quantum computing, to use them, we have to deal with quantum data. And converting classical data to quantum data can lead to information loss. And also, quantum computer is highly sensitive to the environmental disturbance. And this can lead to quantum noise and errors that accumulate during the computation. All of these are making the training of quantum neural networks even more difficult than the classical one. To address this challenge, we combine classical training with quantum evaluation. So in this way, we hope to simultaneously benefit from the classical and quantum system. And about this, operator learning presents an ideal application of quantum neural networks for acceleration. Because as we know, operator learning learns the mapping between infinitely dimensional function spaces. And once trained, these models can repeatedly evaluate solutions for multiple PDEs in the forward paths. The main category of neural networks include integral kernel operators such as FNO, which leverages iteratively learnable kernel integration, and it is usually restricted to grids. And also there are transformer-based neural operators such as GNOT. They have large model capacity, but also relies on sufficient data to achieve better performance. And finally, DeepONet consists of branchnet and trunknet. The branchnet encodes input function as a fixed number of sensors, and the trunknet encodes the location of the solution of PDEs at any point. DeepONets can evaluate the solution of PDEs at arbitrary points, and it does not rely on fixed grid or meshes. So it has been shown that DeepONet is able to handle complex systems, and it has already have a wide range of developments currently. So existing quantum operator learning includes quantum FNO. It leverages quantum Fourier transforms to accelerate parametric PDEs such as Berger's and Darcy's. And by encoding data in unary quantum states and replacing classical fast Fourier transform with quantum Fourier transform, it achieves logarithmic time complexity in PD evaluations, and it significantly outperforms classical FNO in FNO's linear scaling. And benchmarks have shown that QFNO matches classical FNO's accuracy across fluid dynamics and imaging tasks, proving that QFNO has practical potential. However, this study does not analyze quantum noise impact, which is actually a critical gap between real-world deployment on new near-term hardware. The success of QFNO motivates us to explore the possibilities of accelerating other neural operators. So in this work, we will focus on how to use quantum computation to accelerate the evaluation of DeepONet. But before diving into our methods, let's take a step back and learn about the concept of quantum computing. So what is quantum computing? In classical computing, we use bits to represent data, which can be either 0 or 1. However, in quantum computing, we use quantum bits or qubits. So unlike classical bits, qubits can exist in a superposition of states. It can represent 0 and 1 simultaneously until you measure it. And note that in quantum mechanics, the state of system is represented by the quantum state, and we denote it as psi here. And the alpha and beta are complex numbers. We require their square of magnitudes sum to 1. And when we measure the states, we get 0 with probability the modulus of alpha squared, and we get 1 with probability the modulus of beta squared. And things get more interesting with multiple qubits. For a 2-qubit system, the states can be combination of the states can be represented by a superposition of all possible combination of qubit states, like 0, 0, 0, 1, 1, 0, and 1, 1. When we measure this 2-qubit system, we get 4 possible outcomes with corresponding possibilities. Now, let's look at quantum gates, which works similarly as classical logic gates. Here we express a quantum state in a vector notation, here, which is the alpha beta here. And for example, for a single qubit gate, we have the NOT gate. This gate swaps the states of the qubit. So if the qubit is 0, the NOT gate turns it into 1. And another gate is C gate. It changes the phase of the state. And to denote this gate in quantum circuit diagrams, we also have the graphical representation of them. For multiple qubit gates, we introduce the control NOT gate, or C0. It can be represented by this 4x4 matrix, and its effect is to perform a NOT operation on the second qubit if the first qubit is 1. There are many other quantum gates we haven't listed here, but using all of these quantum gates, we can manipulate the qubits in ways that classical qubits cannot do. Before we introduce the whole structure of quantum DeepONet, I want to first introduce the notation used in this talk. So first is the quantum circuit. A quantum circuit usually consists of 3 parts: a initial quantum state, a series of quantum gates, and measurements. So the quantum communication begins with the initial quantum states here, and it is then manipulated by these quantum gates, and finally, after the measurements, the results collapse into a classical outcome based on the probability distribution of the quantum states. And one important quantum gate we are using in this work is the RBS gate. It's a rotation matrix defined by the parameter theta. The RBS gate operates on 0, 1 and 1, 0, while it leaves the states 0, 0 and 1, 1 unchanged. In our approach, we will design the circuit for neural networks using this RBS gate. So we use quantum layer as the building block of quantum DeepONet. It can be viewed as the neural network layers accelerated by quantum algorithm. To handle the classical data on a quantum computer, the whole quantum layer involves 3 steps. So first is to loading the classical data onto the quantum circuit, and then we perform quantum matrix multiplication on a quantum computer, and finally we convert the results back, the resulting quantum data back to the classical data. So now we go through each of these 3 steps in detail. For loading the classical data input, let's say we have a classical input vector x, and the norm of x is 1. We can encode x such that each component of x is associated with a specific basis gate here. And we call this kind of basis states as unary states, because they only have 1 qubit set to 1, while other qubits are being 0. And for example, we have an input vector of size n equals 4. So the circuit for loading this data will look like this diagram here. The first qubit is initialized to be 1, and then we apply a series of RBS gates parameterized by alpha 1 to 3. The final state after the data loader will be the X state here, we listed here. And the value of alpha 1 to 3 can be derived by comparing these quantum states with the classical data input.
Can I ask a question?
Sure.
How did you decide to employ the RBS gates and not other gates? Is it a trial and error, or you did that from the very beginning for a specific reason?
Oh, why use RBS gate, right?
Yeah.
Because it has a parameter that we can tune, right? It has a theta, while other gates I shown before, they don't have a parameter that we can tune. Using this RBS gate, like if we have a theta, we can set the theta as tunable parameter in the following I will introduce. And in this way, we can do the quantum computation or quantum neural network. And I believe if you don't use RBS gate, you can use other gates that also have a two-number parameter. It's also doable.
So actually,
Okay.
the main reason, George, this is Xiu Yang. So the main reason is that because in quantum computing, naturally the intrinsic property is that if we consider computing from mathematical point of view, the quantum operator can be considered as unitary matrix multiplied by some either vector or matrix. So that's why we use a unitary matrix here. So if you go back to the RBS get, that's actually it's a unitary matrix. You can consider that as a rotation matrix. So that naturally aligned with the nature of the device.
Okay, thanks.
Okay. So where are we? So we finished this slide. Let's go on to the quantum pyramidal circuit. And quantum pyramidal circuit in our case is used for matrix multiplication in neural networks. This circuit is adopted from this paper here. And suppose the result Y is calculated by multiplying matrix W with the input X. So the key requirement for this circuit is that the matrix W needs to be orthogonal. And the reason why it needs to be orthogonal is, as we mentioned, quantum gates need to be unitary, and in our machine learning tasks we are dealing with real data. So in that case, it's orthogonal gates. And using orthogonal gates and orthogonal, we build orthogonal matrix, right? And again here, we take n equals 4 as an example. The basic idea behind the pyramidal circuit is to decompose the matrix, orthogonal matrix W into a series of rotation matrix. These matrices are represented by RBS gates, and we arrange them into a pyramid shape. And the angle of the RBS gate here is set as trainable parameters during training. And last part in the quantum layer is tomography, which is used for extract classical data output from a quantum circuit. And compared to other quantum neural network methods, our usage of unary states is particularly beneficial here. Because using unary states, we encode the information sparsely, and it allows us to develop a highly efficient tomography method. And these tomography methods here introduce an ancillary qubit here, and it applies a series of operations after the pyramidal circuit. This tomography procedure allows us to recover the sign and value of the output Y. And specifically, it works like this. So this is the outcome quantum state after applying the tomography. And for sign recovery, we find out if you minus this probability with this probability, okay. And there is another notation here. The 0 here is the state of the ancillary qubit, and EJ here means the Jth unary states we use. So this probability corresponds to the output Yj divided by square of R, where R here is the number of qubits we use. And we find out the sign of Yj can be evaluated if we know the output, know the probability of these two states. And after get the value, we goes back to this equation, and then we're able to get the real value of Yj, which is each column of Y. And now let's analyze the complexity of quantum layer, the primary factor affecting the time complexity of a quantum circuit is its depth, which refers to the longest path from the input to the output of the circuit. These steps indicate how many time steps it takes to perform the entire computation. For example, in this circuit here, qubit 0 first execute a NOT gate in the first time step. And in the second time step, qubits 0 and 1 both execute a CNOT gate. And then in the third time step, a measurement is carried out. So the circuit depth in this case is 3, and which means the computation runs in 3 time steps. And look at our quantum DeepONet implementation, we see that the data loader circuit have a depth of a big O n, where n represents the input dimension. And the pyramidal circuit have a depth of 2n minus 3, but it still scales linearly with n in terms of RBS gates. The tomography circuit is a little bit special. It also has a depth of big O n, but we need to measure the circuit big O n of big O 1 over delta squared times in order to reach a tomography error of delta. Therefore, the overall complexity of the tomography process is big O n over delta squared. So combine multiple quantum layers, we can have a quantum version of orthogonal neural network. And as shown in this figure, the addition of bias and nonlinear operations are performed on classical computers. Building on this concept, in quantum DeepONet, we adapt this idea by replacing the traditional branch net and trunk net with the quantum neural networks. And the additional bias and nonlinear operations are still on classical computers. And therefore, the main acceleration comes from the matrix multiplication in quantum layers. So now let's focus on the complexity of quantum DeepONet and its comparison with classical methods. This table provides the complexity of different phases of the process. The feed-forward path in quantum DeepONet evaluation has a complexity of big O n over delta squared. And this achieves a quadratic improvement in terms of the input dimension if we compare with the classical DeepONet. And for quantum DeepONet training, we keep the complexity similar to the classical method at a big O n squared. And accordingly, our workflow includes 3 steps. First, we train the quantum DeepONet on a classical computer, which handles the training efficiently. And after the training, we transfer the parameters into quantum layers. And finally, evaluation can be executed on quantum computer or simulators. The key advantage of this method is that we can speed up the evaluation phase using quantum circuits. Meanwhile, we maintain comparable complexity during the training. This reduction of complexity is especially advantageous when the input dimension is very large or frequent evaluations are needed.
Can I ask a question?
Okay.
It seems that the biggest cost is the training. The training cost. Why you chose to accelerate the evaluation cost, which is very small anyways?
Because the training using quantum computer is pretty hard, as we mentioned. There are many difficulties that damage the trainability of quantum neural networks. So it's very hard to train on quantum computer. That's why we choose to accelerate the evaluation.
But you can you not follow this flow that you have here, where you can? Oh, I see. No, you say train. I get it. Yeah. So,
Okay.
but I mean, that's the target, right? The target is to actually train on the eliminate the training cost.
You're right. So ideally, we hope we can also speed up the training, but it's difficult for neural network. There are some people doing some linear system, for example. Then we can do the training using quantum computer. But for highly nonlinear neural network with activity function, then doing SGD in quantum computer directly, it's just hard. We don't know how to do it yet.
So actually, yeah, we are developing optimization algorithm on quantum computer, but they're still far away from useful, I would say. Pengpeng will show some result on this impact of noise in the device. So you will see that even in the inference step, because of the noise, it will be inaccurate. So if imagine that if we want to, of course, as I said, our goal is to train the models on quantum computer, but that's still far away. Far away. Yeah, lots of things to do.
Yeah, sure. Yeah, so the issue is actually optimization plus other technical issues. But so you cannot do pins using this, for example.
We cannot train pins, but we can do inference if the model is trained. So far, what people are doing is that, so it's called hybrid model. You have a classical model, trained classical model. You have lots of inference tasks, or maybe you would like to do some reasoning, something like that. So currently people accelerate the inference or reasoning on quantum computer with a trained model.
I see. So maybe the multi-head, we developed these multi-head pins with Zogren that can have like 100 or 1,000 heads or distributions for that. That would be a good pin model to do like this. Okay, thank you very much. Yeah, it's I understand. And also, Xu-Yang, since you're here, maybe because I remember when last time you gave a talk about the noise, I didn't hear anything about the noise except one sentence, but how do we deal with noise? There's no noise at all, right? Because it's done.
So far it's very hard to deal with that. So there are two main ways. One is, I would say more fundamental way is people develop more advanced so-called quantum error correction code. So for example, like you may also read the news that Microsoft, they claim that they can have produce some so-called quantum chips. So which is actually what they did is they developed a new quantum error correction method. So that's a more, I would say, more material science or engineering aspects. For algorithm science, people are also developing so-called quantum error mitigation algorithm. That's basically, I know the data collected is contaminated by some noise. How do I reduce the impact of the noise? So that's the two main ways. But of course, the most fundamental way is quantum error correction. Just like when we design classical chips or when we produce classical chips, of course we try to improve our production techniques or something like that, such that the errors in the chips is as low as possible.
Okay.
We'll show some results on the noise part.
Okay.
Yeah, we will show some results on the noise. Yes.
Okay, great.
Okay, thanks for the question. And next part, since we have covered the method behind quantum DeepONet, in the next part of this talk, I will present our training and ideal simulation results. And by ideal, we mean that we don't consider any quantum noise here. The simulation is carried out using Qiskit simulator. So we first test quantum DeepONet on an antiderivative operator with initial condition set at 0. So here the L represents the length scale of the kernel, and a larger L suggests the input function is smoother. In this example, we explore two scenarios with different length scales. First is L equals 1, which has a test error of 0.9%, and L equals 0.5 with test error of 0.84%. The ideal quantum simulation achieves the same error as classical test error. And this is because essentially when quantum noise is not included, quantum simulation is just the same, using the same math as training. So even though it runs on the simulator, the math is the same. And the second example we test on is the advection equation, and we predict the PDE solution given the initial condition. The initial condition is sampled from Gaussian random field with this kernel, and the error plot here shows the difference between the predicted solution of quantum DeepONet and the exact solution. The relative error for the quantum simulation is about 2% and matches well with the training. For comparison, we also trained a classical DeepONet with the same number of trainable parameters, and the relative error is slightly lower in this case. It's 1.19%. And next, we test Berger's equation, which is a nonlinear PDE. And the relative error for the quantum simulation is 1.38%, which also matches with the error seen during the training. And in this example, we also trained a classical DeepONet with the same number of trainable parameters, and it has an error of 1.05%. While the quantum DeepONet introduced a slightly higher error, the results are still highly competitive and perform similarly with the classical method.
Can you say something about the cost for these methods?
The cost in terms of which
wall clock.
time?
Wall clock.
Sorry.
The wall clock.
We didn't present them in this work.
But what's your was it faster? Which was slower? Which was the same? Because that was the idea, to make it faster.
Yes. In this paper, we didn't use real machine. We simulate the quantum computers by using classical computers. So which will be slow is slow.
I see.
So what time is slow? Because we simulate the quantum computer.
Yeah.
Classical, yeah.
Right. So actually, we showed before, asymptotically, we can see acceleration. Here in numerical test, as Lulu said, because we use a simulator, so we don't we don't compare the time. The one key thing is that we want to see now, because as you mentioned, why we use this very special type of gates. We only use our unitary matrix here. So we want to know if we replace regular matrix with this unitary matrix, what is the performance, right, of this DeepONet, right? Because it's different from our more classical structure.
Yeah, I mean, Xu Yang, the symplectic Hamiltonian systems that we did, this factorization, we did exactly this type of similar factorizations.
Okay, good.
We have not this type of factorization, but same class where you can go like alternate between the upper triangular or triangular, like in the inverted neural networks and so on. And there is a theorem that shows that that's exact and so on. So there are ways to factorize something and make it
flexible for different architecture, right?
Yeah, because we are dealing now with the nuances of spiking neural networks. So
yes. Right.
Why you are trying to, in the emulator you see things are working fine, then you go to the hardware and that's where you are surprised. You find out surprises, and that's that's why it's useful to have an implementation to see what are the bottlenecks actually.
Yes.
Because using lava, for example, to do like SNNs, you get so much out of it. But Chian will work on this stuff with Sandia. I realized that there are, we can solve PDEs in 100,000 dimensions, but then when you try to put on Loihi, Loihi has its own mind. Just like you encounter noise and all these real issues of computing. But I think this this first effort is brilliant, actually. So I
Right.
want to congratulate you all. But please go on. I didn't want to stop the show.
Okay.
Peng, you can go on.
Okay. So we summarize the parameters and errors for all the examples in this table, and including the read steps and activation function learning rates, and the resulting error for different examples we have. And besides, our quantum DeepONet can also be trained using physics-informed loss term. In this case, we don't need any labeled data. And we applied these methods in both the antiderivative operator and 1D Poisson's equation. We found that physics-informed quantum DeepONet is more sensitive to the number of input sensors, and to include more information within the limited input dimension, we use principal component analysis in the branch net. And we set 3 levels of smoothness for each PDE, and these are corresponding error of each scenario. So next part, unlike classical computing, quantum noise is a major difficulty in quantum computing. Therefore, in the rest of this talk, I will focus on the impact of quantum noise on quantum DeepONet. Quantum noise is the random fluctuation that happens in quantum systems. While classical computers can handle some level of noise, quantum computers are much more sensitive. In classical computing, errors typically caused by things like heat or mechanical issues, but in quantum systems, noise can come from many aspects, including imperfect quantum operation, which means not all quantum gates can be applied perfectly due to the limitation of hardware precision. And this can lead to slight error in the qubit states. And the second is the unwanted interaction with the environment or other qubits. Because qubits are highly sensitive to their surroundings. Interactions with external environments like electromagnetic fields can cause the states of a qubit to change unexpectedly. And also, mistakes can happen during the preparing or measuring quantum states. And during computation, small errors from the quantum noise can accumulate, making it hard to maintain accuracy. And managing quantum noise is a major challenge in quantum computing area. And for simplicity, we only introduce certain type of quantum noise in the rest of my talk. So the first kind of noise is the finite sampling noise. When performing tomography in quantum computing, we take multiple measurements, or we call shots, to estimate the probabilities. However, since we cannot take infinite number of measurements, we face a limitation known as finite sampling noise. This is similar to predicting the outcome of a coin flip. So with only a few trials, the results will be noisy and less reliable. But as we take more trials, the predictions become more accurate, and even though there will always be some level of uncertainty. And theoretically, the error decreases with the square root of number of shots. And in this figure, we show the relationship between shots and error using the example of antiderivative operator. The gray line here represents the fitted line of the output, and the dots are the error of each quantum layer in the branch and trunk net. This result matches well with the theory. Another quantum noise we will going to introduce is the depolarizing noise. It's a type of noise that randomizes a quantum state. This noise is parameterized by lambda here, which means that there are lambda over 4 chance to have a change of the quantum states. This can result in 3 types of error, including bit flip error, where the 0 changes to 1, and phase flip error, where 1 changes to -1, or the combination of both errors. Depolarizing noise is widely used when analyzing the variational quantum circuits to understand how noise affects quantum systems during computation. And in this figure, we show the impact of depolarizing noise on a single RBS gate using 100,000 shots. The error, and we notice that the error also depends on the angle theta of the RBS gate, because this rotation will affect how depolarizing noise interact with the states. And that's why there is a periodic fluctuation of the error. So if a quantum circuit includes quantum noise, error mitigation methods can be introduced based on the system's properties. And in our approach, when we load the classical data, we ensure that we are only use unary states. And all the subsequent operations, such as the pyramid circuit and tomography, are also operate exclusively on these unary states. This means that all the operation and information are in unary states. However, quantum noise can lead to invalid non-unary states that doesn't contribute any useful information. To address this, we can only account for unary states during each measurement. So, for example, let's say we measure a state 4 times and get the following results. And we see that there are invalid measurements results such as 0110 or 1001 because they have 2 qubits to be 1 and are non-unary. So we discard them and keep the valid ones here. In this figure on the right, we show the proportion of useful shots at different level of noise and for branch net and trunk net in antiderivative operator. When the quantum noise is larger, it's more likely to have invalid measurement results, and that's why the proportion of useful shots decreases as the depolarizing noise increases. For antiderivative
Can you say
operator
why
example,
sorry, can you go back? Can you say why the trunk is more sensitive than the branch?
in my opinion, it's because the parameter theta in the RBS gate in branch and trunk net are different. And as we shown, no, not this one. As we shown here, right? So even though for the same level of depolarizing noise, when the theta is different, the error is different. So in this case, in branch net and trunk net, you have different parameter theta, and so you have different sensitivity.
Okay, thanks.
Does that answer your question?
Thank you.
Okay. And so for antiderivative operator example, we show the impact of depolarizing noise and error mitigation on the results. On the left figure, which is without error mitigation, and both unary and non-unary states are accepted, we observe that even a small amount of depolarizing noise can cause a large increase in the error. However, on the right, when error mitigation is applied, the relative error remains at much more reasonable level. Additionally, we notice that increasing the number of shots helps to reduce the finite sampling error here. But only when the error mitigation is applied. So without error mitigation, increasing shots does not improve the results significantly. This is because in this case, the finite sampling error is much smaller than the depolarizing error if there's no error mitigation. So increasing shots only reduce the finite sampling error, and therefore it's not very effective. And another interesting experiment we tested is how the network size can affect the error of noise model. For fair comparison, we keep different networks to have a test error of 3%, and we set the noise level and number of shots to be the same for all the networks we have. And we find that the error increases exponentially with the network depth, but it only increases a little bit with growing network width. So it is reasonable because as network depth increases, the error could accumulate between layers. And in practice, if you want to minimize the impact of quantum noise, it is advisable to choose wider rather than deeper neural networks. And there are few limitations of our current implementation. First is the unary encoding actually facilitates the tomography, but it's at the cost of using more qubits. So due to the finite number of qubits and connectivity in current quantum device, our network width is still limited. And also regarding the noise simulation, our current model does not account for coherent and non-local noise. To better understand the resilience of our design, we need to incorporate more complex and realistic noise models. But I have to mention that we indeed use the backend noise model from Qiskit for real device simulation, but the result is pretty large. The error is about 14%. As the quantum device is progressing, currently at this stage, the processor we used is much older than what we have now. So we look forward to tests on newer devices to get better results. And finally, a design that applies nonlinear transformation without collapsing the quantum states can be interesting because it could possibly provide more speed up. So in conclusion, we have introduced quantum DeepONet, a model that could be both data-driven and physics-informed, and it has a complexity scaling linearly with the input dimension. We have benchmarked quantum DeepONet on various PDEs, such as antiderivative operator, the Baktion equation, and Burger's equation. And additionally, we analyzed the impact of quantum noise on performance and explored the effectiveness of error mitigation techniques. And that's all of my talk. Thank you for your attention, and I'm happy to take any questions.
Thank you so much for your great talk. Now we open the floor for questions. Do we have any questions for the speaker? Any comments?
Hi, Pengpeng. This is Raj from Brown. Just had a question on the setup of the gate. So here you have a fine mapping, like you're doing the matrix vector multiplication for a feed-forward neural network. But what happens if you use any FFT layer? Does it, like FNO uses FFT layer, even in evaluation, you need to require to compute the FFT. So how do you incorporate those changes in designing the circuit over Qiskit? So
Let me first So are you saying that can we use quantum Fourier layers in DeepONet?
yes. Yes.
Yes, I think that works. Yeah, you
Raj,
can.
in the paper,
Yeah.
which is page 7, so in this paper, probably if you go to page 7, you didn't show the reference, actually on title, the Jane 2023. In their paper, they have a version of quantum FFT.
Yeah. Okay. Okay.
So
Yeah.
it's doable.
So
In this plot, there's a QFT, which is quantum Fourier transform. On the right hand side, there's an IQFT, that's inverse quantum Fourier transform. So
Yep.
you can there's something called a quantum Fourier transform. So that's a classical existing circuit you can directly use.
Okay. Okay. Thank you very much. Thank
But still, I remember you said that the quantum Fourier transform mathematically is different from
Right,
Yes.
Fourier
right,
transform
right.
in the classical
So it
condition.
depends on. So that's a very good question. So it depends on what kind of Fourier you want.
So you mean that what kind of Fourier means like first Fourier transform or
So
cosine
so in
transform?
classical FNO, right? So you use the very
Yeah.
standard Fourier transform on our
Yes.
textbook. So your basis is exponentials to some power. On quantum, so there's a special version called quantum Fourier transform. It's the basis is not necessarily sine cosine. It's in a different form, which is more, as I said, intrinsically quantum.
Is K an integer still?
Something
Kx is K is an integer,
like
because if it's not, then it goes to a fractional.
Yes.
so because we didn't do FNO in our work, so we just say, okay, we saw people doing this, so and they didn't do noise analysis or something like that. So
Which
we say,
group
okay,
is this, Xu Yang? Which group
I
is this?
think this is some French group, right, Lulu? Is because when we read the
Yes,
paper, I think it's from Europe.
yeah, from French.
French group.
Okay, I will look them up. Okay. I have a question about what is the largest number of qubits that you use in your basis?
so currently, you can see here,
Yes.
the number of qubits is actually the width of our network. So you can see the largest one is 21, but because there is tomography which has an ancillary qubit, so it's actually 22.
Oh, that's pretty high. Can be very complicated, right?
Yeah. So, and it's because we are using unary encoding, it's at a cost of using more qubits to save the tomography cost.
But it's interesting because you show that the noise, you don't pick up noise by increasing the width, right? As opposed to depth. So
Oh, sorry, what?
You show when you talk about the noise, you show that. I didn't know that. Okay, so the width is actually the number of qubits. So as the number of qubits increases, the noise does not increase. I thought that's what you showed, right? There was an L2 error.
I think what she shows that the error increases more significantly when depth increases versus
So that's what I'm saying.
increases.
But the width you said here means the number of the basis elements.
So okay, one of the catch here is that because we use a simulator, so on simulator we cannot exactly mimic the noise on a real device. So there's some existing noise model on some simulator, so we only use that. So, but of course, those noise model cannot fully reflect the true noise on the device.
Okay, because it's a little surprising that I expect that just like orthogonality, when you increase the number of basis elements, you will have more trouble, more noise, right? Think of Chebyshev going high order.
Right. So you can see that when the width increases, noise is increasing but slowly.
Very slowly, yeah.
Yes.
But how do you explain why the noise increases with the depth then? Exponential.
I think so. Like if you think every quantum layer have the same level of noise, so if you have more quantum layer, the error is accumulating exponentially. So like from layer to layer.
Okay.
Okay, thank you. We have another question from Dr. Wahid from Fudan University. Can you please comment on the cost of data loading and how it affects your inference cost?
Cost of data loading. the cost of data loading is actually ON, and it's negligible compared with the tomography. So now tomography is the dominant.
Dr. Rahi, did you get your answer? Do we have any other questions for the speaker?
Lulu, where did you have you published this paper yet?
It's on the review at the journal Content.
Okay, great.
Yeah,
Good
second
luck.
round review. We submitted
Good luck.
last year.
Yeah, good luck. It's very good work. It's excellent work.
Oh, thank you.
Pengpeng, you gave an excellent talk. I didn't know anything about quantum, and now I know very little, which thanks to you.
Yeah,
Google
thanks
will
for
be a
your
PhD student
compliment.
at Yale on this fall.
Okay.
Oh, very good,
great.
very good.
Okay, I think we don't have any other questions. Thank you for your great talk. It's time to close the session. Thank you everybody for joining us today, and I hope everybody has a great weekend ahead. Bye.
Yeah, thanks. Thanks for the opportunity. Bye.